Swayam Prabha. Digital India. Educated India.
So we had started on that in the last class. Full wave, bridge, rectifier. So we mentioned that this circuit will consist of 4 diodes and whatever load it is, RL load or R load, and this is going to be connected to the AC source, right? So we said that we would number this as D1, D4, D2, D3, and here is the AC source. So I am calling this as A and this as B. During positive half cycle, A will be positive, and during negative half cycle, B will be positive, right? And we said that the path will be from A to D1 to RL, and then it will go through D4 and back to B. So this is during positive half cycle, and during negative half cycle we'll start from B because this will be positive now. So B, it will go to D2, from D2 it will go to R and L. So again the current will flow only from up to down, and then it will go through D3 and then back to A, right? This is the path. So we drew the waveform also, if you may recall, in the last class. So this is going to be the sinusoidal waveform, and I told you that it will start off from zero current and slowly build up. That's what we said. So once it builds up and the minimum values are almost remaining the same, and similarly maximum values are remaining almost the same, we are going to call that as the steady state. So if it is a purely resistive load, I am going to have the rectified waveform somewhat like this. The voltage waveform will be somewhat like this. This is the rectified voltage waveform, and current will exactly follow whatever is the voltage wave shape. So I am going to have essentially the current wave shape somewhat like this. This is how the current wave shape is going to be. So this is I load for pure resistance. If it is a purely resistive load, it will touch zero, obviously, because the voltage is touching zero, the current also has to touch zero, right? Whereas if it is inductance, obviously the current will not touch zero because it would have already accumulated energy. The inductance would have accumulated energy, so it will give back some of its energy, and because of which the current will definitely be retained above zero value, because we are going to have always Ri plus L di by dt equal to whatever is my input voltage. If it is Vm sin omega t, then I am going to have 0 less than or equal to omega t less than or equal to pi. Whereas if I am going to have Ri plus L di by dt, this will be equal to minus Vm sin omega t, because it is the reverse of the voltage that is being applied when I have D2 and D3 conducting. So I am going to have this to be 0 less than or equal to omega t less than or equal to rather pi to 2 pi, right? This is how it is going to be. So always the inductance will find at least some amount of energy to be stored as long as I am going to have Vm sin omega t or magnitude of Vm sin omega t being greater than Ri. If it is greater than Ri, always inductance will try to store energy. If it is less than Ri, it is going to be, the shortfall is going to be met by the inductance stored energy. That is how it is going to function. So you will never see that the current really touches down to zero value. It will never touch down, zero. That's what is going to happen in this case. If higher and higher inductance values are seen, you would see that if this is the voltage, that is the supply voltage, the rectified voltage is somewhat like this. I am going to have actually the oscillation in the current is really, really minimized. So I may have something like this, then it may increase, again decrease, again increase, decrease, and so on. You can see that the current will essentially see very, very minimal oscillations if I have a larger and larger value of inductance. Higher the inductance value, the ripple in the current will decrease because the inductance acts like a filter. Whenever there is a shortfall in the energy, it is going to supply back. So the amount of energy supplied back is going to make the current fall or current rise really, really minimal. That's what is going to happen. So this kind of waveform, that is the load current waveform, is going to be true for high L, larger value of inductance. This is how the current is going to be. Now, because I will have D1 and D2 conducting, D1 and D4 conducting during this portion, I will have the current flowing in this direction. Whenever D1 and D4 are conducting, we had already said from A it will flow to D1. So the current direction is this way. So during positive half cycle, I am going to have the current exactly flowing from here to the load. So if I say this is what is the supply current direction normally I take, then I am essentially going to have the current, whatever I mark here in blue, until this portion, right? This is going to be the current during positive half cycle. Whereas during negative half cycle, I have to have exactly the opposite of the current, like this. So I would see that if I look at the current on the AC side, if I try to look at the current, I am going to get exactly the current, whatever I have got in the load, exactly being reproduced as it is until the positive half cycle. In the negative half cycle, whatever is the load current I am having, just the opposite of that, negative of that, coming up as the supply side current. So I will have positive current and negative current equally visualized on the supply side. So there is no question of any saturation of transformer. If I put a transformer on this side, it will have equal amount of fluxing and defluxing. So there is no question of the transformer just accumulating the flux and then getting saturated. It will never happen. So you will not see any saturation in the case of a full bridge rectifier. This is one of the major advantages of full bridge rectifier. In most of the applications, we may be using transformers because we might have to bring down the voltage to the required level. That may be done with the help of a transformer. So generally, whenever you use a transformer, you look for such a configuration where you will not have saturation. So full bridge rectifier is a good, apparatus for being used along with a transformer. So much so for diode bridge rectifiers in single phase. So let us now go to controlled rectifiers. So in controlled rectifiers, I should be able to determine at what point I want the device to conduct, which means I have to use a controllable device. If I am using a controllable device, I should be able to give a gate pulse, firing pulse, only at that instant when I want that to control. So I will be able to get a variable DC voltage. Whenever I have a diode rectifier, I don't have really the liberty to control the output DC voltage. Whereas whenever I have a controllable device like thyristor, I will have the capability to control the output voltage. So let me start off with half wave controlled rectifier. So I am looking at a similar circuit. Only thing is I am going to replace this diode by a thyristor. That's all is the difference. Right? This is a half wave configuration, but I am going to replace this particular diode what we had put earlier with a thyristor, and I am going to show the load like this. It can be resistive, it can be RL. Either way is fine. So this is going to be the controlled rectifier configuration. So if I actually have my sinusoidal voltage somewhat like this, right? I can choose to make this device conduct by giving a gate pulse at any point in time. But clearly, for an SCR to conduct, I have to have two conditions being satisfied. One is it has to be forward biased. The second one is I have to give sufficient gate pulse. And of course, after giving that, the current has to exceed the latching current value. Only then it will continue to conduct. So I may choose to probably fire it somewhere here. Maybe which is like 35-40 degrees. So I am going to give the gate pulse only at this point. I will not give the gate pulse before that. So if I give a gate pulse at this point, let's say this is the angle normally specified in all the textbook as alpha. Alpha is the angle of conduction or at which I am going to give the pulse to the thyristor. So this particular angle is delay angle or firing angle. We call this as delay angle or firing angle. The delay angle is the angle at which I am giving the gate pulse, which is delayed from 0 degrees. So the conduction is delayed by so many degrees, whatever is the delay angle I am actually doing the design for. So this alpha is known as delay angle or firing angle. Right? This is completely under my control. I can always have a firing circuit, right, or the control circuit, control electronic circuit, which I can design to give it at any angle alpha, 30 degree, 40 degree, 90 degree, before 180 degrees, of course. If I try to do it beyond 180 degrees, clearly this device will be reverse biased. I am essentially planning to make this device conduct not from 0 degrees but beyond 0 degrees. So I will give the firing pulse only at a later time than 0 degree. So if I give it at 0 degree, it would have started conducting right here. There will not be any difference between a diode and an SCR. But if I delay the conduction, obviously it is not going to start conducting at this point because I have not opened up the gate. So it will start conducting only from this point. So at this point it is going to start conducting and I am going to get this as the output voltage. Had it been resistive load, I would have gotten the voltage only until here, because the current would also stop exactly at that point. Whereas if it is R and L load, I will have the current starting from this point. I should again show at this point the current will start. But the current cannot jump to a large value right away because it is RL circuit. So the inductance current cannot jump from 0 value to a large value right away. So the current would slowly start rising. It will rise. And until what point it will rise depends upon, again, what we wrote as the equation, if you may recall, Vm sin omega t equal to Ri plus L di by dt. This will be the governing equation. And this is true for when I am going to start from alpha. Originally we wrote 0 for diode, but now I am going to start from alpha until pi, depending upon whether it is R load. If it is RL load, I may have beyond pi also, right? So this is going to be until the conduction takes place, maybe pi for R load, maybe until beta for RL load, right? So the current will start like this and then it will probably die down at some point, depending upon where exactly the current starts falling, how much is the stored energy in the inductance and so on and so forth. So if I try to draw the voltage corresponding to this, I may have some voltage waveform somewhat like this, right? The same current I am drawing with multiplied by R. If I try to only look at the voltage across resistance, so this is going to be IR. This is I, for example, right? So whatever is the leftover voltage here, the difference between these two, that happens to be VL. This happens to be L di by dt or VL, whatever is the voltage across inductance. Because I am essentially writing that Ri plus L di by dt equal to Vm sin omega t, and this is Vm sin omega t and this is IR. So obviously this has to be L di by dt, right? It will be reversed, yes. See, if I am writing Vm sin omega t, it is still Vm sin omega t, only thing is omega t is now greater than pi. So automatically it becomes negative. I don't have to reverse it forcefully, right? So I am going to have now, after this, IR is somewhere here. So if I try to look at IR and Vm sin omega t difference here, this happens to be the VL value which is in the negative direction now. You get my point, because we are having essentially Vm sin omega t smaller than IR. So IR minus Vm sin omega t becomes minus VL now, because of which I am going to get this as the negative inductance voltage, or I can say instead di by dt is becoming negative. So the current is falling during this portion. So L di by dt happens to be negative because the inductance is now trying to give back its energy. Until I was increasing or di by dt was positive, inductance was storing the energy. When once it has reached the peak and Vm sin omega t equal to IR, there is no more energy that can be given to inductance. So now inductance is switching in and it is trying to give back some energy. So it joins hands with the voltage source to make sure that the resistance needs are met. That's what happens. So this area, if I say L into minus di by dt, and these two areas have to be equal to each other, because inductance cannot really hold back any energy with its own self. I may go to 0 at this point. At this point, I will go to 0 because it is starting from 0. I have shown it as though it is starting from 0 because it is a half-wave rectifier. In the full-wave rectifier case, it can be different. In the diode, we saw that the current never touches 0. Right? Only in the pure resistive load, it touches 0. So in this particular case, yes, it is touching down to 0 value because I am not applying any more voltage. Here my thyristor gets reverse biased. So if I try to look at the output voltage corresponding to this, I will have the output voltage somewhat like this. I have to have the output voltage somewhat like this until the current really becomes 0. So this entire thing is going to be my output load voltage. This is going to be my load voltage. So it starts from alpha, but it goes until beta. So at alpha, I am going to have again the current to be 0. At beta also, I will have the current to be 0. So I have to essentially solve the complete differential equation, look at the regular, the particular integral, and then I should be able to say at what point, that is initial condition will be I of alpha equal to 0. And the final condition beta can be solved for by putting in the same solution for I of beta equal to 0 and solve for beta. Yes. Why there is a? I want to control the voltage. If I don't have a delay, if I don't give a delay, I will not be able to control the voltage. Previously in diode rectifier case, I was starting the conduction right from here. So I got only a value of Vm by pi for a resistive load. This was a constant. And in the case of inductive load, I had to start from 0 and go until beta, and I had to say Vm sin omega t d omega t. So this point is not controllable, right? Whereas here, I am able to control that. So I would be able to control how much voltage output I am getting, right? So this is essentially for controlling the output voltage. You are not controlling the voltage. You are either giving a gate pulse or do not give a gate pulse. That's it. If you give a gate pulse, you are going to see that the device starts conducting. If you don't give a gate pulse, it will not conduct. That's it. Right? So let us now try to take a look at, now that we have seen at least half wave rectifier, let us now go to the full bridge controlled rectifier. Yes. If you are going to have the inductance forward bias this thyristor or a CR, even after the positive half cycle is over, you are still having this device connecting the source to the load, whether you like it or not. So whatever is the source voltage, it will appear across the load. Why not? Right. But we are looking at the overall voltage across this. We are not segregating IR and L di by dt. We are putting it together. So these two are exactly in parallel. So whatever is the voltage here will appear here. Got it? That's the reason. Right? Yeah, we will come to a full bridge, then you will know even more. We will come to a full bridge rectifier, controlled rectifier, because half wave hardly ever we use. We hardly ever use. But just for continuity, I took it. That's it. So let us try to take a look at fully controlled bridge rectifier. So I am going to have again 4 devices. But all of them are going to be thyristors. So this is going to be connected to a load. Right? And I'm going to have the AC supply connected here. Right? So let me again name these things. This is T1, this is T4, this is T2, this is T3. Okay? And let me name this point as A, and this point is B, and I'm going to have this as the load. Right? Maybe I can say R and S. These are the points. Okay. So let me first of all start with drawing the voltage waveform. So this is my voltage waveform. Right? I don't want T1 and T4 to conduct at this point because I want to have a control. So which means I have to delay the triggering of this particular device by some angle alpha. So I'm going to trigger T1 as well as T4 simultaneously. Both of them will be triggered simultaneously. I will give a gate pulse for both of them simultaneously. So I might have had the current carried over from the previous half cycle. That is very much possible. or I may be starting from 0, depending upon how exactly the circuit is working, whether resistance is dominating, whether inductance is dominating. Depending upon that, I may start off with 0 current, or I may start off with some finite value of current. Very clearly, if I am starting from rest, the current would start from 0. It cannot start from, some finite value. If I am starting from rest, the current will definitely start off from 0 value, right? So let us say the current has started off with 0 value. Maybe it is going like this, right? And then it is reaching some maximum value somewhere, and then it is going to probably come down. Maybe. Right? Because I am essentially having T1 and T4 conducting still. They are going to conduct still until I give a pulse for T2 and T3. So T2 and T3 pulses I may give only at this point, because if I want it to be symmetrical, I have to give it at pi plus alpha. Very clearly. I can't have them to be completely unsymmetrical. If I try to make them unsymmetrical, I will have the positive half cycle voltage maybe much higher than the negative half cycle voltage, or vice versa. The moment I have positive half cycle higher than negative half cycle or something, I will not have even kind of voltage being applied repeatedly. Similar kind of voltage being applied repeatedly. So I would normally fire, if one of them is fired at 30, for example, 30 degrees, the other one will be fired at 180 plus 30, 210 degrees. So I will always have them fired symmetrically. So if it is fired symmetrically, let us say in this particular case I have shown as though the current has reached 0. Then again the current has to start, and it might probably reach the same value and then again come down. This is how it is going to be if it is highly resistive, very small inductive circuit. The inductance is really, really small, not good enough to sustain the current for much longer. If the inductance is really strong enough, it would have stored sufficient energy to pull along the conduction for even from 180 degree to 180 degree plus alpha. Even during that time it would have pulled along. So if the inductance is not sufficient enough, I am definitely going to have only a smaller amount of stored energy, because of which it will not be able to pull along for too long. Just to show this, I can show it somewhat like this. Maybe I am going to have IR drop to be very, very high. Like this I should show. IR drop is very high. So I am going to have maybe the inductance voltage only this much. Only this much is the inductance voltage. Right? Actually I have not drawn it very well. So I should have on the other side, the negative of the inductance voltage should be this much. You get my point? IR minus whatever is the supply voltage. Vm sin omega t equal to again IR plus L di by dt. So I should say L di by dt equal to Vm sin omega t minus IR. So this is Vm sin omega t. And this I have shown as I times R. So whatever is the difference, that is inductance voltage. So inductance voltage is the shaded portion. This shaded portion should have been equal to the other shaded portion. One is minus VL, the other one is plus VL. I have not shown it exactly that way, but that is how it should be. Whatever VL is accumulating, right? Inductance is accumulating as energy. The entire thing has to be given back right away. So that is what is making the current continue into the negative half cycle side as well. So if I try to look at the voltage during this kind of a conduction, I am going to have essentially the voltage actually coming out somewhat like this. It would start at alpha and it is going completely like this, and it would go until, if I may call this angle as beta, it will go until beta. This is how the voltage waveform is going to be for one half cycle. It starts from alpha and goes through pi and goes into the negative direction until beta. Now again for the next half cycle, it will start from pi plus alpha. So if I may call this as pi plus alpha, the next one is pi plus alpha. Again it will go through this and it will go until here, which is pi plus beta. So I'm going to have this kind of voltage waveforms repeated. This is across the load. You get my point? Yeah. No, not at all. Beta is here. Pi plus alpha is here. So let me probably remove this and say this is beta. Beta is here, where the current ends. The current is ending at beta. And after that only I am trying to fire D2 and T2 and T3. You get my point? Yes. Yes.
Why are we firing at 5 plus?
Because I am firing this at alpha. Why are we firing that at alpha? Because I want to get a control over the voltage. Let me try to now get what is the average voltage. But you want it to be symmetrical. Now if I draw the current waveform, it will be symmetrical. If I try to draw the supply current waveform, right, I will have this to be the current on the supply side and this to be the negative half cycle of the current on the supply side. They are exactly symmetrical. So it is starting at alpha, ending at beta. It is starting here at pi plus alpha and ending here at pi plus beta. Supply side current. Based on inductor, will alpha have a limit? No, it doesn't have to. We'll look at that. Continuous conduction case we'll see. This is discontinuous. The current is discontinuous on the DC side. The load side current is discontinuous. You get my point? What we mean by discontinuous is it is touching zero. So we call this as discontinuous load current. So this will happen when R is dominating. When R is dominating over L, this is going to happen, right? So when I have R dominating over L, the inductance stored energy becomes really minimal. Because the inductance stored energy becomes minimal, I would not have the inductance sustaining the current because the inductance has to supply the energy. If it doesn't supply the energy, the current will not be sustained. Please understand, the moment this point is crossed, pi is crossed, I will not have T1 and T2 anymore forward biased by the supply. The supply cannot forward bias it, right? So only way to forward bias the devices is if I have an inductance here, then instead of having plus here and minus here when it was absorbing energy, now when it is releasing energy, it will become plus here and minus here. L di by dt, di by dt has reversed its direction. Current has started falling. Because current is falling, I will have essentially plus here and minus here. And look at this plus. This plus is connected to the anode here. So because of which T4 will get forward biased. Similarly, this minus is connected to T1's cathode. So obviously, T1 and T4 can get forward bias if inductance voltage is sufficient enough to forward bias these two devices. Right? That is the reason why we are having the conduction possible through T1 and T4. And remember, only when T1 and T4 conduct, my IS is flowing in this direction. When T2 and T3 conduct, the IS will flow in the opposite direction. Get my point? The supply current will reverse its direction if I am switching over the conduction from T1 and T4 to T2 and T3. Because T2 and T3 will always have the current flowing like this. You are looking at, this is the way the current is going to flow. T2 and T3, if the current is flowing, this is how it will flow, which is in the opposite direction. This is in the opposite direction. It cannot flow in this direction, like what I showed earlier. Shall we go over to continuous conduction so that let's see whether we have understood the discontinuous conduction properly? This is discontinuous conduction. The current is starting from 0. If by chance I didn't have such a high IR drop, maybe resistance is small, right? In which case, I am probably going to have my IR drop. I'm just drawing it arbitrarily. It may be somewhere here only this much. This is what is IR drop. In which case, it gets much more energy to be saved in the inductance. If IR drop is smaller, I will have L di by dt component to be much larger. So it will save much more energy in the inductance. You think about it this way. If I had 10 ohm resistance with a 400 volt supply, I would have gotten only 40 amperes of current. So half Li square, if I try to calculate, I square will be only 40 square. If I use only 1 ohm resistance, then I would have 400 amperes of current. So half Li square will become half L 400 square. So obviously I am going to get much more energy stored in the inductance. So lesser the resistance, I will have more energy stored in the inductance, clearly. So if I am going to have much more energy stored in the inductance, why would the current end here? The current can definitely sustain itself for longer, right? So let us try to look at that kind of a waveform which is corresponding to continuous conduction. So I am going to have the voltage waveform like this, right? And I am saying continuous conduction, which means the current cannot start from 0. It has to start from something other than 0, a higher value. Of course, it would have gone through initial transients. It would have started from 0, inductance would have accumulated more and more energy and so on and so forth. And ultimately, it would have reached a steady state where I minimum and I maximum are at some fixed values. That is the way it is going to be. So, let me draw the other half cycle also inverted or rectified. Let me choose again a firing angle, some alpha, and let me say this is pi plus alpha. Okay? Now, the current is starting from some non-zero value. It is starting from some non-zero value. So, it is going to increase maybe until some point, I don't know, and then it will start decreasing. It is not linear, obviously it will be exponential, and the RL circuit. At this point, again, I am firing the next two devices. So at this point, I am firing 1 and 4. Whereas at this point, I am firing 2 and 3. Right? So when I fire 2 and 3, let me probably again draw the circuit so that it is, this is 1, this is 4. Here is where I am having A, and this is the AC source with positive half cycle like this, and then it is going to go through the load. It is coming through 4, and then it is going to return like this, right? This is what it is. This is corresponding to 1 and 4, right? At this juncture, I am going to have here anyway 2 is sitting, but it is not conducting. Similarly, I am going to have 3 is sitting here, and that is also not conducting. Both of them are sitting here, right? Now, until here it is very clear. Until pi it is very clear, I will have definitely 1 and 4 conducting. After that, let me write the equation again. Vm sine omega t minus Ri equal to L di by dt. So wherever I am going to have, Ri probably is equal to this. So at that point I am going to have the current start declining. So if Ri, if I say this is I times R, whereas this is I, so wherever IR is equal to the supply voltage, the current will start declining after that point. So the current starts declining at that point, right? Now, when the current starts declining, I'm going to have, if I show this as separate inductance and separate resistance, I'm going to have very clearly plus here and minus here. So the inductance stored energy is going to aid whatever is the supply voltage as long as it is still in positive half cycle, because in positive half cycle I'm going to have plus here and minus here. So this plus comes in addition to the source. Both of them come additive. They become additive as long as positive half cycle is persisting. So during positive half cycle, this plus is actually added to this plus and minus of the voltage. So together they are able to forward bias the overall devices, although IR drop happens to be quite high, right? Both of them together essentially make up for the forward biasing of the device. Now, as it comes beyond pi, still I have to retain the conduction in the same direction. The property of inductance is to retain the current direction as much as possible by virtue of its stored energy. So, this will now strive hard further to forward bias these two devices still, despite the fact that the voltage supply has gone into the negative half cycle. So the voltage supply has gone into negative half cycle, all right, but the inductance stored energy still is going to dominate over IR drop and this supply voltage, both of them, to sustain the conduction, despite the negative half cycle being, there. So, I will have the current continuing, but it is still declining. The current is still declining. So, the inductance is still having some amount of stored energy, definitely. But at this point, I am trying to fire 2 and 3. Because I have come to pi plus alpha, automatically 2 and 3 will be fired. When 2 and 3 are fired, which one is more conducive for conduction? That's what we have to check, right? Whether 1 and 4 are more conducive for conduction or 2 and 3 not, I have to check, nature will check, basically. So what happens is something like this. 1 is conducting, which is like a short circuit. 4 is conducting, which is also a short circuit, right? So because of these becoming like short circuits, and now I have come into negative half cycle, which makes this as positive and this as negative. So this is the negative half cycle, right? Now, because this is a short circuit, this positive is applied automatically here. And because this is a short circuit, this negative is applied automatically here. You get my point? This is positive, this is automatically applied here, and that is negative. Through device number 1, it is automatically applied to the cathode of device number 2. So that device is forward biased. So what happens is, because of the existing conduction, this negative is applied here this positive automatically comes here. So this device is forward biased. Similarly, if I try to look at this particular device, this negative comes here and this positive comes through the short circuit of this here. So this device, if I may call as T2, this as T3, both T2 and T3 are forward biased because of the conduction of the previous thyristors. Now I have two thyristors forward biased and I apply a gating pulse. Immediately they will take over. Why not? The moment they take over, they kill the other two thyristors. You apply the same logic. The moment these two take over, those two will become short circuits. Right? Once they take over, they are short circuits. If they are short circuit, I'm going to have this plus applied through this to this terminal. Right? So I'm going to have, let me draw this again. So I'm going to have, these are the four devices. This is T1, this is T4, this is T2, this is T3. This is negative half cycle, mind you. So I'm going to have plus here and minus here. This is negative half cycle, right? Now I'm going to have, I'm not unduly bothered about the load. T2 has taken over, I have given it pulse. T3 has taken over, I have given it a pulse. Now, this is plus, so automatically I'm going to have plus here. This is minus. This minus is going to be connected through this to the minus here. T4 gets reverse biased. So, the two devices which helped T2 and T3 to get into conduction, that became suicidal for those two devices. So T1 and T4 helped T2 and T3 to get into conduction, but after getting into conduction, T2 and T3 quenched them. They said, go to hell, that's it, turn it off. That's what happens. Right? So, this particular current transfer from T1 to T4 to T2 to T3, that has taken place because of the supply voltage reversal automatically. The supply voltage reversed from the positive half cycle, it came to negative half cycle. So, if I had fired it anywhere here also, T2 and T3 would have taken over without any difficulty. But I chose to delay it by alpha, pi plus alpha. That is the reason why T2 and T3 are taking over much delayed. But the moment T2 and T3 take over, T1 and T4 go off because they are reverse biased by virtue of the supply voltage. The supply voltage is the one which is coming across those two devices to turn them off. So, this line voltage which helps the commutation or turning off of the thyristor is known as line commutation or natural commutation. The other one what we discussed earlier with LC circuit and diode and so on, that we forced. We told the circuit that according to this design, you are going to have a reverse voltage at this point in time. Here we don't have a control, it is at 50 Hertz. So 10 millisecond it will be in positive half cycle, 10 millisecond it will be in negative half cycle. So I don't have any control over when it reverses or something. So the moment the voltage reverses, it is ready for being turned off. But I chose the moment when I turn on the other two devices because of which they went off. But I didn't do anything further. I didn't deliberately apply a negative voltage. By turning it on, automatically the negative voltage comes across the device. So I don't have to do anything special. So it is natural commutation or line commutation. Yes.
T1 and T4 will be reverse biased. That will be based on whether the voltage across the inductor is greater or the supply voltage is greater.
If I am having inductor voltage and supply voltage like this, they are opposing each other. Agreed. But I didn't even draw any load. Please note, even without any load, I am able to simply apply only the supply voltage across T1 and T4. Forget about the load. You know, there is no responsibility of the load here at all. I have not even shown the load here. You see? Because these two terminals are directly connected across T1 and T4. This is for negative that is connected to the anode directly. And this is positive that is directly connected to the cathode. The load does not come into picture at all here. So when there is continuous conduction, I assume the devices to be short-circuited. Whichever device is conducting, that is short-circuited. So the load does not really come into picture at all here when I am talking about the commutation in continuous conduction. The load is completely this side. I have not even drawn it, and it doesn't matter.
But it will affect now because whatever voltage is across the inductance, that is the positive side of the inductance is direct.
But that doesn't matter because the supply voltage is coming across the device. The load does not come into the circuit at all now. When I'm talking about forward biasing or reverse biasing, the load is completely an isolated, separate circuit. I may form the loop probably through T1 and T4, or I may form the loop through T2 and T3. But this is a separate loop in itself. Right? That is a completely separate loop. You get my point? So this is an independent loop, completely. So whenever I have continuous current, I do not have to worry about what the load voltage is. Absolutely. I don't have to worry about it at all. All I need to worry is only whether I am able to fire a particular device. To fire a particular device, it should be in the corresponding half cycle. If I have to fire 1 and 4, it has to be in the positive half cycle. If I have to fire 2 and 3, the firing has to be done only in the negative half cycle. Otherwise, I cannot really do that. So, now if I look at the voltage for this, the load voltage, I'm talking about load voltage. So, this current will repeat itself. This current will repeat itself. If I try to look at the load voltage, I should have from alpha until pi plus alpha, again pi plus alpha to 2 pi plus alpha, and so on and so forth. This is how the load voltage waveform will be. Right? Obviously, I am having 1 and 4 conducting through and through until here. 2 and 3 conducting through and through until here. Right? So, I should be able to write the expression for average voltage. Output DC voltage average. This will be Vm sin omega t d omega t 1 by pi from alpha to pi plus alpha. Am I right? So, this if you calculate, it will come out to be 2 Vm by pi cos alpha. And if I vary alpha, I am going to get different values of voltage. When alpha is 0, I will get maximum. So that full voltage comes across the load, and when I am going to have higher and higher values of alpha, lower and lower values of DC voltage will appear. So, what is the application? If I want lower value of armature voltage to get a lower speed in a DC motor drive, I can increase alpha, right? I want to have a controlled rectifier feeding a DC motor drive. The DC motor drive speed is dependent upon how much armature voltage I am applying, right? I hope you remember at least some amount of machine. EB is proportional to K phi omega and EB is equal to VA minus IARA. IARA drop is very, very small. So I can say VA is approximately equal to EB. And EB is proportional to phi omega. So if I keep the flux as a constant, as I increase voltage, omega will increase. As I decrease voltage, omega will decrease. So I can always obtain whatever speed I want, according to the voltage that I apply. So vary alpha smoothly, you will be able to get variable speed. This is one of the typical applications of, the converter that is being applied for speed control. It can be for battery charging. I can control the current that is going into the battery. If I want very quick charging, I have to really impress upon the battery a huge amount of current. A lot of research is going on in battery charging because of electric vehicles. So there, normally it takes 6 hours to 8 hours to charge a battery of the vehicle. Two-wheelers, that is the major problem. The maximum distance you can go is 40 kilometers. So you go 40 kilometers and after that you have to wait for a charging station. And charging station these days will take at least currently it will take 6 to 8 hours to charge a battery, right? So you can't really think of going anywhere until completely the battery is charged. So power electronics research is going towards increasing the rating of these rectifiers which charge the battery. So you want to push 300 amperes, 400 amperes of current in one go. Can we do that? Whether the battery will be able to withstand that, whether our rectifier will be able to deliver that much. So a lot of research is going on towards that particular area. So this is one of the applications of rectifier. So we will look at, I don't want to pump in more because you guys probably should look at it. I hope you will look at it tonight so that tomorrow when we start on the next topic, in the same thing continuing, it will make sense, right? So we will look at our LE load, which we have not seen as yet, which is like a DC motor drive because back EMF will be there. And after that, we'll go over to semi-controlled and uncontrolled and so on. Semi-controlled and with freewheeling diode and so on.